Okay, thanks everybody for coming. I'm pleased to introduce Daven Henze from the University of Colorado, where he is an associate professor in the Department of Mechanical Engineering. He holds a PhD from California Institute of Technology. Prior to joining the faculty at CU Boulder, he was an Earth Institute postdoctoral fellow at Columbia University, where he worked at the NASA Goddard Institute for Space Studies. Is that where Jim Sanson is?
He was.
Okay.
He's emeritus now.
Okay. His research focuses on air quality, long-range pollution transport, and climate change. A large part of his research stems from chemical data assimilation, the process by which both models and observations are combined to produce estimates of the atmospheric state that are often more complete than those provided by either approach alone. This encompasses more specific interests in remote sensing, adjoint sensitivity analysis, inverse problems, and source apportionment. Dr. Henze has received an EPA Early Career Award, a NASA New Investigator Award, and several university awards for teaching and research. He is the lead scientist for the Geoschem Adjoint model, a member of the Geoschem Steering Committee, co-chair of the Hemispheric Transport of Atmospheric Pollutants Working Group on Source-Receptor Relationships, a member of the EPA Clean Air Scientific Advisory Committee, and a member of multiple NASA satellite science teams. So, pleased to welcome Daven Henze, and hope look for a good talk.
So thank you, John. It's nice to be here talking to many familiar faces and some new faces. I'll be presenting work that's done in collaboration with several colleagues, as well as work that's done by Forrest, who was a PhD student in my group before he was postdoc here. So maybe you can ask him all of the hard questions. Really, this will be a survey of several different studies that we worked on in this past year, with the connection really being a sort of methodological connection in terms of how we use remote sensing data and how we use sensitivity analysis to look at the sources that contribute to different aspects of air pollution problems and the interaction of air pollution with ecosystems and the interaction of air pollution with climate. And so, many of you have seen these types of famous figures before that really highlight some of the areas that we have of concern for air quality and in regulating air quality. These pictures show the outflow of pollution from urban areas out over other land areas and water bodies, and this highlights the fact that air quality is sort of something that has a very broad spatial scale, and that air pollution transport is something that's a big concern when people are thinking about controlling air pollution. The prevalence of this amount of pollution in populated areas is currently estimated to be leading to upwards of 4 million premature deaths per year. This is in the top 10 risk factors of disease that we know of, and this is accounting for upwards of 8% of all non-accidental deaths per year. So this is a really something that is on the radar of the sort of global health community. And when people make these estimates, they're largely attributing most of these deaths to exposure to the fine PM2.5, which is really what you're seeing in these satellite images. You're seeing the long-range transport of the PM2.5, but there's also, of course, exposure to ozone and the long-range transport of ozone. The fact, though, that you can see the PM2.5 from these satellite images is an indication that it's interacting with visible light. And the other consequence of that is that these species are impacting climate change. And so because of that, they've earned the name short-lived climate pollutants. They're long-lived enough to blow out over the ocean, but they're not long-lived in the same way CO2 is long-lived on decadal to century timescales. They have lifetimes on the order of weeks to a month for the aerosol components, or maybe a decade for methane. These pictures here highlight the role that addressing air pollution mitigation might potentially have on strategies for mitigating global warming, but also on domestic air pollution health impacts. So on the left, you have projections going out to the year 2100, following various scenarios in which either strategies are focused exclusively on CO2, or strategies in which you focus exclusively on these so-called short-lived climate pollutants, SLCPs, in particular focusing on sources that are rich in the components of SLCPs that have a large absorbing or a warming component, such as black carbon and methane. And then also the combined strategy of addressing both. So what you see is that to really cause some near-term action in these projections of temperature change, some change to the precursor emissions or the direct emissions of the SLCPs are required. To really change the final value that this projection is headed towards over the course of 100 years, of course, we need some action on CO2, having a lot more climate inertia there. But on the right-hand side, we have some numbers that provide additional incentive for thinking about controlling these pollutants in the near term, which is, again, the benefits of these controls via air quality at the domestic scales and at the sort of, as I mentioned, the near-term scales. So these plots, these bubble plots here on the right, show for the SLCP mitigation scenarios plotted on the left what the annual avoided mortalities were estimated to be in each country named by these bubbles. So in some countries, approaching, saving potentially 1 million lives per year. And this is a very tangible, immediate public health benefit that a lot of governments find motivating and potentially more compelling than the plot on the left. But maybe this is, the plot on the left is sort of what we would view as a co-benefit that could come out of policies that are driven by an air quality human health concern. They may be able to be designed in order to have residual co-benefits for mitigating climate change. So overall, I'll be talking a little bit about some of the methods in our group that we use to look at these kind of questions, and then run through a couple studies where we've applied these methods. One is looking at the national scale impacts of abating emissions from cookstoves. The next is looking at the impacts of diesel emissions, particularly the NOx emissions from diesel vehicles in 11 major markets in the world. And then lastly, going back to this question of the role of PM2.5 versus ozone in terms of its influence on the global burden of disease from air pollution, and some updates to our understanding of the role of ozone and the impacts of ozone on human health. So starting out, the first part is, again, sort of a survey of some methods that we use in our group. There's been a lot of studies over the past decade or going back even further that have tried to, on a global scale, evaluate what are the health impacts of air pollution. And they're doing this using global models because globally we don't have enough in situ measurements to quantify air pollution throughout the world. And a challenge in these types of studies is that the models that are used to simulate air pollution at these scales are typically performed at resolutions shown on the plot on the right. The grid cells have lengths on a side that are 100 or 200, 250 kilometers. And then part of this estimation process is to align the gradients in pollution with the gradients in population. And a typical map of population is shown on the left, and you see that there's sort of a scale mismatch. Like the gradients in population are much finer than the gradients that we're able to resolve for the concentrations, which is to say that when we estimate the human health impacts of this air quality, we're lumping in, downtown Manhattan with eastern Pennsylvania, and that clearly we know from just our knowledge of this region that air pollution and air quality in these two parts of the country is very different. So there's been some studies that have tried to quantify the impacts of this coarse resolution approach to quantifying exposure. And essentially these studies have taken high resolution models and then run them at coarser resolution or regridded them to coarser resolution. And at every step along the way, gone back and recalculated what is the impact of PM2.5 or individual components of PM2.5 on premature mortality. And so all these plots are sort of pegged on the left to the estimate of premature mortality associated with exposure to aerosols that you would get with the finest model that they considered. So the one on the study on the left started with a 12-kilometer scale CMAX simulation. The study on the right started with a half-degree scale geochem simulation, and then moved to coarser and coarser resolutions. So what you see is by the time you get out to the resolution of the global model studies, sort of 250-kilometer scales, is that you're underestimating exposure very significantly, maybe as much as 40% for exposure to the primary particulates, such as black carbon, less so for some of the secondary particulates whose distributions tend to be a little bit more spread out. And you might even be overestimating exposure to natural components, such as dust. This is a bias that has been quantified via these studies in the US, but when we think about these types of biases contributing to our understanding of the global burden of disease, we don't necessarily know that it's always going to be an underestimation. We don't know that it's always going to be a low bias because this artifact comes about from the relative positioning of the population centers and the sources of these pollutions. And in other parts of the world, you get a lot of pollution from different types of sources of pollution than we have here in the US. And so I think that these types of plots just generally show you how much uncertainty there might be in a global study of the burden of disease from PM2.5 associated with these types of global models. And that's motivation for thinking about better ways that we might be able to address those types of questions globally. And so a piece of information that we've used a lot in our work comes from Randall Martin and Aaron Van Donkelar's progress at Dalhousie University in translating information from aerosol optical depth retrievals from a variety of satellite instruments into maps of PM2.5. And so these are a combination of several different satellite measurements with some model simulations that relate column AOD to surface PM2.5 calculations, and then these are calibrated according to in situ measurements, and they use some other geographical and geostatistical information to generate these maps that are shown on the right that are at more of the 10-kilometer scale. And so a nice feature of this is that they're able to estimate surface PM2.5 concentrations with a consistent uniform methodology throughout the entire world. And so this has led to, I think, a greater understanding of what is the global burden of disease associated with this amount of PM2.5. These maps contribute directly to these numbers that we quoted earlier about the 4 million, et cetera. That was based in part on maps like this. These maps have also been used to develop concentration and response relationships, so to help learn about the relationship between exposure to PM2.5 and hospital visits in areas where there wasn't previously enough in situ measurements to help with the epidemiological studies to refine that relationship. So this is a map that we've been using, but the science of how do you use satellite data to constrain surface PM2.5 is a scientific area that's evolving. And as this field continues to evolve over parts of the world, they're developing maps that are resolved at the 0.01 degree scale, so getting down to sort of kilometer scale variability as detected from space. And then in the future, we will be looking forward to updated maps that will be based on more recent or upcoming satellite missions. So they're starting to use data from VIIRS to inform these. Hopefully in the future, we will have tropomi, and eventually in the large parts of the northern hemisphere, geostationary satellites that would help us, have a picture of how this changes not only in space but in time. So this is my cartoon on the left. This is sort of, I think where I was at as far as being able to estimate exposure in my models as a graduate student. In the middle, that's what Forrest was doing. And in the future, hopefully in a couple of years, we'll really be able to be looking at this in high resolution space, but also, you see an additional dimension there, which is how do these concentrations evolve in time, and can we constrain that from space? And I think that will also provide a lot of insight into the global burden of disease as well as concentration response relationships. So we use these maps in a few different ways. What I'm doing here is I'm pulling out one grid cell from our global model at the 2 by 2.5 degree scale and showing the subgrid variability that is resolved by these kind of remote sensing derived products. And then I have this expression over here on the right, and we break this expression down into two terms. One is a downscaling component, where we take our model value and we multiply it by the ratio of the satellite derived value at the fine scale to the satellite derived value averaged at our core scale. So this is just saying, well, 80% of the PM might be over in this corner, and a very small amount of the PM might be over in that corner where it was actually all over the ocean, et cetera. And then we also have this term here, which is the ratio of the satellite data averaged at our model to our model value, which is essentially a bias correction in the model. So we're adjusting our mean model value over this large grid cell. And this is essentially giving us back the fine-scale satellite product, which here we have plotted against the population gradients that you saw earlier to try to show that we're making some, I think, improvements in aligning the scales here to do a better estimate at quantifying exposure. The other tool that we use a lot in our group that I'll be talking about is Adjoint modeling. We use this for source-receptor analysis. And I think the best way to get across the benefits or the differences between this approach or of this approach are to compare it to forward model sensitivity analysis, which you might be more familiar with, Forward model sensitivity analysis is wherein you look at a bunch of sources, potential sources in your model, and you run one model simulation, and then you go back and you run another model simulation, say you target industrial emissions, and you perturb those a little bit, you reduce those, you run the model forward, and you see how does concentration change in different parts of your model. Here's how much it impacted the PM in the cities, here's how much it impacted the PM in the rural areas. That is the attribution of that PM to this one source that was just considered. As you start to go consider different scale or different sources, you want to know, well, what was the role of this factory versus that factory, or transportation, or biomass burning? You would need to run additional perturbation experiments to quantify those source attributions. Conversely, adjoint modeling is a receptor-oriented framework for looking at source attribution. So first we consider a particular receptor function or receptor metric. So here we'd say exclusively focus on PM concentrations in the populated areas, and then ask how does that PM depend upon all of the different sources. And so we'll run a variational calculation which considers a perturbation in concentration there and maps the contribution from all of the different sources to that particular receptor. So here we're getting information about all of the different sources that contribute to population weighted concentrations in one city. If we wanted to consider, say, different cities or different countries or different receptor metrics, we'd have to run this calculation over and over again. So the cost scales with the number of receptors that we consider. The benefit, though, for any one receptor function, such as what is the global burden of disease associated with exposure to PM2.5, that's the number we've been talking about, we can map out the contribution from all of the different sources and the cost of one forward model run and one adjoint model run, which costs about 10 times the amount of running one forward model simulation, but we're getting about as much information as we would from hundreds of thousands of forward model runs. So it's really just kind of a neat computational trick that we borrowed from the oceanographers and we're using to play aerosol games with. Okay? So as I mentioned, the single receptor metric that is of interest in this context is, again, this number, this 4 million deaths associated with premature mortality. We're interested in knowing what are the aerosol emissions that contribute to this. And so with one adjoint calculation, we can focus on this particular receptor metric. And this is a paper written by Colin Lee, who was a graduate student with Randall Martin at Dalhousie. And the maps here show the contributions of different aerosol precursors to this global burden of disease. So they don't show the global distribution of deaths associated with PM2.5. That's sort of what, when we see these maps, I know we kind of want to see that map like, oh, there's the distribution of deaths associated with ammonia. That's not what we're showing. We're showing the contribution, so the change in deaths per kilogram per meter squared emitted associated with different emissions of ammonia and different emissions of nitrogen dioxide, black carbon, or sulfur dioxide. So this is telling you how much do the emissions in any location contribute to this global burden of disease. We're not necessarily saying where these people are dying because we care about all deaths equally in this framework, and so any death is counted equally. But at some point, somewhere in the world, in this calculation, there would be a premature mortality associated with the change in emissions. And so this paper was highlighting that some of the largest sort of per kilogram deaths per change in emission were associated with emissions of ammonia. And you also see very large sort of per kilogram deaths associated with emissions of black carbon, so because it's a primary species. In also particular parts of the world where the baseline mortalities are quite high, and so exposure to additional levels of PM exacerbates sort of a pre-existing susceptibility to this type of disease. Another single global metric that we're interested in, getting back to the original discussion of, say, air pollution versus climate, is our metrics that we use to compare the climate impacts of different anthropogenic processes. And so one number that we think about a lot is radiative forcing, right? This has been a very useful metric historically in IPCC reports for quantifying what is the impact of different constituents in the atmosphere, what is the impact of different anthropogenic activities in terms of the Earth's radiative balance. People have slowly refined that radiative forcing bar chart to go not just from like what is the radiative forcing of different atmospheric constituents, say aerosols versus CO2, but to look at the radiative forcing of different activities in different parts of the world. So refining What is this radiative forcing associated with emissions from North America versus South America versus Europe? Or what is the radiative forcing associated with different emissions from different sectors, or maybe emissions by different species? So looking at biomass burning versus domestic biofuel, or say different modes of transportation, the plot on the right showing rail versus aviation, shipping, or road transportation. So these are helping refine that radiative forcing bar chart in a way that's more directly applicable to people making sort of policy decisions than, say, a map that, or a bar chart that said aerosols contribute this much. So the idea was to apply the same approach that we're using adjoint sensitivity analysis to apportion this response metric to contributions from each of our aerosol emissions and our aerosol precursor emissions in different parts of the world. So essentially we get a radiative forcing bar chart with a different bar in every grid cell of our model for every different aerosol species and sector. And we're able to map out the variability in the sort of watts per meter squared per amount of aerosol emitted. You can see, imagine that as sort of the radiative marginal damage of different types of aerosols. And this varies quite a bit. This radiative forcing efficiency varies by more than an order of magnitude as you look around different parts of the world. Say this is a map of the radiative forcing efficiency for black carbon. If you're near the equator and you have emissions of black carbon that are going to go out over the ocean where the albedo, the ocean's rather dark already relative to black carbon, that black carbon emission isn't having a huge radiative effect as much as it is if it's emitted over a place where there's not very much deposition, or where the transport is going to be of this black carbon over very bright surfaces. So you see these latitudinal gradients, and you also see gradients here, I think, that are driven by changes in black carbon lifetime and just the transport of black carbon over surfaces of different albedo. So unlike, say, emissions of CO2, it really matters when we think about the role that SLCPs might play in some sort of mitigation agreement or emissions trading program. It would really matter where these are emitted as far as the role that they're going to have. So the work that Forrest did was to take this another step further and to look at not only the direct radiative effects, but try to quantify what are some of the ranges of variability in these in terms of the indirect effects and the secondary effects of aerosols via their interactions on clouds. So this table on the right is showing a range of scaling factors developed from a comparison of multimodal studies that have sort of mapped out our understanding of the uncertainties of, for example, you take black carbon, the interactions of black carbon beyond the direct radiative forcing, so the interactions via its impact on clouds, might be a cooling, might be a warming. There's a range of studies that show either method. So we're applying sort of a range of scaling factors to these studies, and we're propagating these errors. We're propagating these range of values all the way through our calculations. And then added to this, we looked at the radiative forcing of black carbon emissions via deposition on snow. So taking, again, a multi-model mean estimate of the total radiative forcing associated with black carbon deposition on snow of about 0.15 watts per meter squared, and attributing that to different emissions based on their potential to actually deposit black carbon on snow. Lastly, when we're talking to people in the kind of policy, co-benefits, decision-making activity arena, they're not so interested in radiative forcing. They want to know, how is this going to impact temperature? They want to know, how is it going to impact temperature in their backyard? Well, we probably can't tell them that. But we might be able to say something about how these numbers translate into large-scale estimates of global temperature change. And so what we're using here are values that are called absolute regional temperature potentials. These are basically derived from a series of perturbation studies in the GIST climate model, where they imposed different radiative forcings in different latitudinal bands and saw how temperature responded in different latitudinal bands. And this basically is a coefficient for translating radiative forcing into an impact on temperature change, when we're looking broadly at sort of temperature change across these large latitudinal bands shown here on the left. So then Forrest used these coefficients to map from our radiative forcing efficiencies to a temperature change efficiency. So now we have a plot in the upper right, which is a map of what is the impact on global mean surface temperature per emission of black carbon. if you had a map like this, again, for CO2, it would be like the same color everywhere. The fact that it's not the same color everywhere is telling you that, the impact of black carbon on temperature change really is a function of where is that black carbon being emitted because of its heterogeneous impact on radiative forcing. But there's also a heterogeneous climate response to radiative forcing given the timescales of these radiative forcing from short-lived species. So moving forward, the questions that we were looking at was, okay, how do we, what studies are looking at sort of spatially distributed impacts of emissions in terms of their impact on climate? And Forrest focused in on a study looking at cookstoves. There's been a lot of studies already looking at the impacts of cookstoves, largely on indoor air quality, and we know those are quite severe. And there's been impact studies focusing on the greenhouse gas emissions associated with emissions from cookstoves. But the gap that was kind of missing was a uniform analysis of both the health impacts from the ambient air quality of cookstove emissions, as well as looking at the greenhouse gas and aerosol impact of the cookstove emissions. There have been a few studies right around the time that we were working on this that were also looking at the climate impacts of biofuels in general. And different studies were sort of getting different signs for the answers, saying, well, that maybe if you remove biofuel absorbing aerosol emissions, this would cause a warming and some would cause a cooling. And again, this is related to that range of values that we saw for the interactions of these types of aerosols with clouds. So we tried to develop a framework to analyze this, first by developing an inventory of cookstove emissions, and then by following this modeling process that we just described, go from an emission of a primary aerosol species to an impact on temperature change by doing this adjoint sensitivity modeling with geochem, and then using these parameterized climate model calculations to translate that into a change in temperature. So propagating some of the uncertainty in that process through led to this figure, which I think helps explain why there was a variety of studies out there showing that cookstove emissions might be causing a warming or they might be causing a cooling. And because, well, I'll explain this plot here. What we have is the global surface temperature change, equilibrium surface temperature change, after complete removal of emissions from cookstoves. And on the bottom axis is our estimate of the black carbon to total carbon ratio. And on the vertical scale is the temperature change. And then we've got different parallelograms spanning this. And each of these different color parallelograms corresponds to different assumptions about the radiative impacts of black carbon. So if you have very strong warming impacts from black carbon, if you remove the black carbon associated with cookstoves, you get a big cooling. Conversely, if black carbon itself has not a very strong warming, or in fact a cooling, then you remove this black carbon and you'll get a warming owing to the removal of the organic carbon as well. So we're looking at the impacts of black carbon, but then in each of these parallelograms, this is modulated by similar uncertainties in the organic carbon. So you have the black carbon, that's the absorbing component, and the organic carbon, that's the reflective component. And we're estimating a mean value that is a slight cooling associated with removal of all of these emissions. But we can definitely see that within reasonable assumptions about what emissions ratios would be, or our understanding of the interactions of these species with the planetary physics, that we could easily end up in a space where you end up with a cooling or a warming. All right, so it could go anywhere from a 0.16 degree warming to a minus 0.3 degree cooling for removal of black carbon emissions, or removal of carbon emissions from cookstoves. Then we looked at this at the country scale. So what if you were to remove the cookstove emissions in just a particular country? We can do this because if we've apportioned these effects at the grid scale using our adjoint sensitivity analysis. So this allows us to say what are the impacts by country. Again, this is the impact on global temperature. This is not the impacts on temperature in individual countries. This is the impact from emissions in individual countries on global temperature. And when you look at the uncertainties associated with these uncertainties in either the radiative effects or the emissions, you get this range of values that often spans the axis here, that often spans the the zero line, which is to say, in any one country, we're not really all that certain across different modeling studies whether you get a warming or a cooling from removal of emissions of cook stoves. Of course, when you remove emissions of cook stoves, you don't just remove emissions of organic carbon and black carbon. There's other co-emitted species. In some parts of the world, they're using fuels that are also going to have emissions of SO2. And then there's the greenhouse gas emissions that are associated with cook stoves, as well as some of the shorter-lived species like NOx. And so we added to this in Forrest's subsequent study the additional species that are emitted. So looking at SO2, CO2, CO, methane. Again, estimating the radiative forcing of these species is a little more straightforward because they're well mixed, and we don't have to look at these types of detailed simulations of their radiative forcing efficiencies varying in space. But again, we're using some parameterizations of climate models to translate from radiative forcing to impacts on temperature. And so we use this to estimate the temperature change associated with removal of cook stove emissions. On the left is shown a removal of cook stoves globally, and then on the right, a snapshot in 2050 of removal in cook stoves at one country at a time. And we decided to do these calculations in sort of a transient fashion. So rather than pick a particular time horizon and say, well, let's focus on global warming potential in 10 years or global warming potential in 100 years, let's just estimate how temperature would change over the course of these decades. Because if you have an interest in the near term, then what you'll find is that it's really the carbonaceous, it's really the aerosol species, the short-lived species that drive the temperature change. And if you have an interest in the long term, it's the greenhouse gases. So we thought we'd just plot all of that. And so the scenario that Forrest constructed here was a phase out of the cook stove emissions over the first few decades. And so you see this large response owing to what's shown in gray and green. These are the aerosol, primary aerosol species. And then over time, the yellow signal kicks in. That's the impact from the removal of CO2. So by the time you get out to 2050, the aerosol and greenhouse gas components are almost balanced in a way. But still, the uncertainty in the total radiative forcing associated with our uncertainties in the aerosol indirect effects is now, by 2050, almost completely swamped by the magnitude of the signal coming from the greenhouse gases. And so we think that when you account for all of the species, it really does appear to be a clear sort of climate benefit to have a cook stove mitigation scenario that should be thought favorably from a climate mitigation perspective. So the greenhouse gas impacts are largely overcoming the potential downsides of removing the organic carbon. Then lastly, we go back and add this piece that we showed before. We had this map from Colin Lee's paper showing what are the impacts on health per amount emitted. So now we have the impacts on temperature per amount emitted. We can combine that with the impacts on health to estimate for the same removal of cook stove emissions, what are the impacts on mortality, and do what's called a co-benefits analysis. Some studies really try to put all of this on the same axis by then monetizing all of these impacts. And we decided not to do that. We decided to just plot, well, first I'll show you the health impacts, and then I'll show you kind of both, our approach of looking at both simultaneously. So this is the impacts on global premature deaths owing to removal of cook stove emissions in each of these countries. And the different colors in each of these pie charts show you what species is largely driving, or what species are associated with the magnitudes of the premature deaths avoided. So this is largely being driven by the removal of the primary organic carbon, which is contributing a lot to the PM mass generated by these cook stoves. And then we tried to, as I mentioned, do sort of a co-benefits analysis where you look at both of these axes side by side. So rather than put them on the same axis, we just plot them on both. And what we're showing here is the per cook stove contribution to temperature change on the axis at the bottom, and then on the top, the per cook stove contribution to premature deaths. So we've normalized this in each country by the total number of cook stoves in that country. Otherwise, you just see bubbles that correspond to the magnitude of cook stoves in that country, and you just see one really big bubble for China. So this plot is providing guidance if you have, say, some policy that is looking to mitigate cook stoves but has a limited amount of resources. They can't just go in any country address all of the cook stoves in that country, because that could be a very different number of cook stoves depending on which country you look. But they say, okay, we have a fixed amount of cook stoves that we're going to replace with some other stoves, or a fixed amount of money we're going to spend on this problem. Where would you spend that money to kind of get the most bang for your buck as far as co-benefits in terms of a climate mitigation and avoided human health consequences? And so what we're seeing here is that countries like Azerbaijan, Ukraine, Kyrgyzstan, Kazakhstan, which aren't ones that are typically targeted in these cook stove mitigation studies, had very large co-benefits for climate because they tended to have northern latitudes. They tended to be contributing to absorbing aerosols that would then transport up to higher latitudes where the climate response is more sensitive to radiative forcing. And they might be over surfaces that have brighter albedo. And then also these tended to be in regions where there was a very high per amount emitted health impact response owing to very high baseline mortality rates. Another way of looking at this was to just sort of rank the top 20 countries according to the impact on climate, according to the impact on health, again, focusing on ambient air quality, and just the magnitude of the emissions themselves. And you see that there's, in this Venn diagram, the sort of the nexus of all three of these converging on about a dozen countries that have very large emissions and potential co-benefits for climate and health, again, focusing on the ambient health impacts. There's, of course, I think in any of these countries, tremendous health benefits to be reaped from cleaner cook stoves, from indoor air quality. So to summarize, we're using satellite data to help us ask these questions on global scales, to be able to use global models and to refine our estimates of exposure. And we're using remote sensing data to do this, and we're also using adjoint modeling to allow us to attribute these impacts, such as global change in mortality or global change in temperature, to emissions from specific countries. And one of the results that we found from the study is that the cook stove mitigation in countries with high baseline mortality rates, black carbon-rich fuel mixes, and favorable geographic locations have sort of pronounced co-benefits for both climate and ambient air quality. The next part, I promise the parts get shorter at each part, so this is not another half hour. Okay. Using these similar types of tools to look at the impacts of excess diesel NOx emissions. So this was a project that came about through collaboration with Susan Annenberg and colleagues at ICCT, the International Council on Clean Transportation. The folks at ICCT were interested in looking at quantifying diesel NOx emissions. And particularly they were doing some literature studies to estimate the magnitude of diesel NOx emissions that were what we'll call in excess. So emissions that were higher than the certification limits in different markets around the world. And so they focused on the 11 markets shown here on the right, where we plotted the diesel vehicle sales. Because if you study these 11 markets alone, you've essentially captured 80% of the global sales of diesel vehicles. And we're focusing on diesel NOx as a particular sector because if we look at global NOx emissions, about a third of that comes from transportation, and about a half of that comes from on-road diesel sources. So this is a pretty significant fraction of anthropogenic NOx. So ICCT was doing literature reviews of different types of studies that have done remote sensing studies or more direct measurements of emissions in active vehicles of the NOx emissions. And these are based on studies in China, Europe, Japan, and the US that have been conducted over time for cars, trucks, and buses. And what they're showing with these black lines in each set of four is for different countries what the regulations, what the permissible amount of NOx emissions were in different countries as they progressed in ratcheting down their emissions control standards, or their emission standards. And then here in red, they're showing what they estimate from the literature review, the actual emissions changes to be. And so if you look at somewhere like the European Union for cars, while they were going from Euro 3 standard to Euro 4 standard to Euro 5 standards, they were expecting a factor of 3 decrease in the NOx emissions from diesel cars, but in practice they were seeing no decrease in emissions. So these excess emissions that you're seeing here in red for the cars, these are largely associated with these illegal defeat devices that were allowing these vehicles to pass tests, but then in their real road performance to be emitting quite a bit more. The excess emissions shown in red for trucks and buses aren't associated with illegal defeat devices as much as they're associated with sort of inconsistencies between the testing conditions that we use for certification and the way these vehicles are operating in real world conditions. So then we added up all of these emissions across these 11 markets, making some projections based on different types of vehicles in different markets where those literature reviews were not conducted, to estimate what the total emissions were from cars and trucks. And so let me walk you through this plot. The solid line here is the total emission currently from heavy-duty vehicles, and then the dotted lines are the total emissions from cars. And the red colors are what we think the total are, and the yellow colors are what we think the total would be if everybody was actually matching their emission standards. Right? And so the gap between these is, again, this excess amount of emissions. So what we see from this is that under current emissions levels, the excess amount of emissions is quite large. From the heavy-duty vehicles, this is 45% higher than the standards. For the light-duty vehicles, it's almost a factor of 2 larger than, or a little more than a factor of 2 larger than the standard. Overall, this means we've got emissions that are about 50% higher than our standards globally.
Is the increase seen as time goes on just because there'll be more vehicles?
So yeah, and so then in terms of how this changes in the future, the baseline scenario is sort of our best estimates of how these things would develop given current on-the-book standards. And so things are decreasing in the near term owing to implementation and enforcement of current standards, and then ultimately they start to rise later on as population and vehicle miles traveled increases. This could be changed under sort of alternative scenarios that were explored by having countries adopt additional standards that are not currently on the books. So essentially everybody adopting Euro 6 standards, which would really cause dramatic decreases in these projections. Having people adopt what are called RDE standards, so real driving emission standards. So these are programs that test in service vehicles, monitor emissions, cover a broader range of driving conditions, and allow for independent verification of emissions as applied to the light-duty vehicles. So that's having the impact shown in purple here. And then lastly, what we call next generation standards. Basically, if everybody had to comply with California's voluntary standards, then you can pretty much eliminate diesel NOx emissions relative to where we are now. Then we broke down the impacts of these different emissions on human health by market and by the permissed amount versus the excess amount, and then also showing heavy-duty vehicles versus light-duty vehicles. So again, this is our present-day estimates. That the dark line shows the permitted amount of NOx emissions, and this.
Annual?
This is annual. This is the estimated premature deaths associated with exposure to PM2.5 and ozone annually coming from this much NOx emissions. And then the pink and red shows you the excess amount. And that's, again, it's broken down by the pink, that's the heavy duty, the trucks and buses, and red, that's the light duty vehicles. So a few things to note. When we look at this globally, about a third of the premature deaths that we're getting from diesel NOx emissions are associated with the excess emissions, right? The red and the pink. And then overall, of that excess, about 3/4 of that is associated with the heavy-duty vehicles. And that's true in most of these markets around the world, except for Europe, where it was dominated by the Dieselgate, right? You had these illegal defeat devices, and so this was dominated actually by the excess emissions from the cars. In the US, we also got some attention for Dieselgate, right? There was this, see it? You see it? See that really thin red slice right there? There's several studies that came out to show that there's probably about 100 premature deaths per year owing to illegal defeat devices in the US. We just don't have that many Volkswagens here. But we do have trucks and buses, and those are causing a factor of 10 larger problem, and a legally permitted problem at the moment, but something on the order of about 10,000 premature deaths per year owing to just inadequacies in our enforcement of our existing diesel NOx regulations. So that's the pink line for the US. So this could be improved. This could certainly be improved, as we mentioned, by adopting Euro 6 standards in countries that have yet to do so. So you get the largest improvements in avoided premature deaths by adoption of these Euro 6 standards in China and Mexico and Brazil. And then further enforcement of additional standards such as the RDE and next generation standards in Europe and India. So globally, this could be avoiding by 2040 close to 200,000 premature deaths per year. And so this is as not a result of this paper alone, but as a result of a lot of attention being drawn to this issue because of the illegal defeat device issues, but other studies that have pointed out the pollution associated with the sector. Last year, mayors of 8 major cities in the world said that we're not going to allow diesel vehicles in our cities by 2025. London is starting to impose additional taxes if you want to park a diesel vehicle that's older than that's from 2015 or earlier. It costs more to park in London. Volvo announced this past summer that they were going to stop producing new diesel vehicles. It's just too expensive to try to match regulations. They'd rather just make hybrids and electric vehicles. In terms of co-benefits, that was all about the air quality benefits. This is kind of a busy table, and I think really I can summarize it quite quickly. There's a lot of potential climate impacts from changing NOx. You change NOx, you can change aerosols, you can directly change ozone, you can change methane. Methane is going to feed back and change ozone. There's a lot of little effects, and Forrest very carefully went through and added them all up, and they added up to a little bit warming or a little bit cooling, but not something that was a big number. If we look at the total change here, this is in terms of milliwatts per meter squared. These weren't huge numbers compared to some of the rated forcing numbers that we looked at previously. So we're not anticipating a big climate disbenefit from removal of these NOx emissions. So again, to summarize the key messages here, presently excess diesel NOx emissions may be contributing to about 40,000 premature deaths globally. This is largely driven by trucks and buses, unless you're looking in Europe. In the future, we could avoid close to 200,000 premature deaths annually by enforcing additional standards, such as Euro 6 standards globally. And the climate disbenefits of this in terms of, you're removing some nice cooling reflective aerosols is probably not huge and probably something that we could live with. Okay. Last chapter, and again, I promise these get increasingly short. So in 3 minutes or less. This was a paper that went back and looked at our estimate of the health impacts of ozone versus PM. And there's, as you've seen, the numbers that I've reported today, there's these estimates that say, 4 million or so premature mortality is associated with air pollution. It's largely driven by PM2.5. And a lot of these global studies, as well as the regional studies that the EPA conducts, will find that about 70, 80, 90% of the health impacts of air pollution in the US are driven by PM2.5. And the numbers that they're using these days are all based on one study from Jared et al. That is used to quantify the long-term health exposure risk associated with ozone. And it comes down to this one number derived from American Cancer Society stat, which is the effects estimate for respiratory illnesses, which goes into this function that is used to estimate premature deaths. So it's really the basis of many of these studies that we've just discussed. But in this paper, we went back and looked at a paper that came out this past year that went and looked at the same cohort, the same American Cancer Society study, but looked at it more recently. So they had more additional 4 years of data to study, and in those additional 4 years, a lot more people have died, which gives them a lot more statistical power to quantify these epidemiological relationships. So this one little number that goes in that function has gone from 0.004 to 0.011. It's gone up by a factor of 3. In addition, they had the statistical power to identify a significant association of long-term exposure to ozone to cardiovascular diseases. It's not as large as the association with respiratory diseases, but a lot more people die from heart attacks than they do respiratory diseases. So you have a little effect on heart attacks. This could add up to being a really big number. So they're able to find these again because they just have more data points, but they're also using estimates of ozone exposure that come from, in addition to in situ measurements, they're also using modeled ozone surfaces. So they're able to get estimates of ozone exposure across broader swaths of the population. So when they add all this up, when we add all this up, we apply these functions globally and go back to this sort of global burden of disease estimates, where previous studies have estimated several 100,000 deaths associated with ozone. Now for respiratory illnesses, we're making this estimate here about close to 1.25 million premature deaths associated with ozone from respiratory illnesses. And we don't like to add these two bars together because they come from very different effects and they're very different as far as their uncertainties. But if this turns out in other studies to be a robust effect, there's potentially another 1 million premature deaths associated with exposure to ozone per year. This means that ozone would be sort of on par with PM2.5, potentially upwards of 2 million deaths or more per year associated with ozone, whereas current estimates are a couple 100,000. Right? So this could increase our sense of the impacts of ozone by up to a factor of 5. Which would mean all the studies that I just showed you would need to be redone. And all the studies that you've seen that would say, look at the impacts of, say, what is the environmental impacts of implementing, electric vehicles. You're shifting emissions from on-roads to power plants, and they do the monetary analysis of all that. This could be very different if all of a sudden the impacts of ozone were being underestimated by a factor of 2 to maybe a factor of 5. So that's really the take-home message there, is that potentially I think it's going to be very interesting to keep an eye on this epidemiological information that's coming out to see if this really revises our understanding of the benefits or impacts of different emission strategies in terms of their impacts via PM2.5 and ozone. Okay. So with that, if there's any more time, I will take questions on any part of that. Thank you. Yes.
How do you get the data of people's exposure to, say, how much ozone? Do you make the data from measurement, people wearing them?
We put them in this little room, and no. So this is all statistical associations. They track. This is just tracking hospital visits in a cohort of several 100,000 people in many different cities in the U.S. over several decades. And then they control for their weight, were they smokers, did they have other illnesses that may have given them some predisposition or some risk towards dying. And then they look at how much of the variability in the number of the hospital visits was unexplained by all the known risks. And then they do a lot of statistical analysis of that compared to the variability in ambient concentrations of ozone in these different cities. And those ambient concentrations come from EPA monitoring, and in this study from Turner et al., some of those values also came from modeling studies. So this is an epi study. It's followed up with, there's some more controlled studies in sort of the toxicology literature of, mechanistically understanding why ozone would lead to an increase in respiratory illness. And I think that's on fairly solid ground for respiratory illnesses and not so much for cardiovascular influences, which is why we try to keep those numbers separate, and they have very different uncertainties.
I recently have heard someone's work in Asia to actually make people wear a device. Would that be more accurate, or in any way set a comparison to be done to see how wildly different this might be?
I think that, there's a lot to be learned from personal exposure monitoring in terms of being able to better refine these effects estimates in terms of, like here, we have one effect estimate that we're applying to all people in the entire world, which assumes that all people have essentially the same susceptibility to ozone. And that, from studies that have looked at different sectors of the population, we know is not true. It's just an assumption that's made for lack of any other consistent basis to do this analysis globally. So that type of personal exposure monitoring is really useful for, say, identifying how this might be different from one segment of the population to another, or for, say, particulate exposure, where if you're exposed to particulate matter in this part of the city versus that part of the city, you're probably exposed to chemically very different particulate matter. And that can lead to different effects estimates, say, for aged black carbon than fresh sulfate.
You took actually away my answer, because I wanted to ask about the cohort study. I assume was over the US, and then you use those factors to estimate the global health impact.
Yeah. So, yeah. Yes.
It seems a little counterintuitive to me that because the Euro standards have been such a roaring success, emissions in Europe that we would want to encourage anybody to adopt.
Well, it's, I'd say, adoption plus enforcement.
No, but Europe, so far, there is no Dieselgate. No one in Europe has actually broken the law, in the way I understand.
Right. So, let me
Even
go back
though
to
they
the
all
slide.
perform the way VW's doing in Europe.
Okay. So there's, I think, a desire in the RDE scenarios to implement on-road testing and certification by somebody other than the automobile makers, which is part of that scenario. And that, I think, would go a long way towards alleviating that loophole. I don't know as far as legally, the design of the policies, how that might be implemented in other countries, but there's definitely a lot of talk in places outside of Europe that are considering, as I mentioned, just a straight up ban, which is something that, defeat device or not, if you can't have the vehicle then in cities, then that's just one way to sort of circumvent that loophole or close that loophole. Yes, Sasha.
If I could lead back from policy to spectroscopy, the one advantage or benefit that we show organic aerosols is that they're fairly coming out of combustion are white and therefore reflect sunlight. But I keep forgetting about brown carbon. And also my experience when I look at the fire, initially the smoke is blackish, and then after some time, if you follow it on an airplane, becomes whitish, presumably because aerosols become more hygroscopic and start adding water layers to start the light. So you had one reinforcing, I think, diagram that had the organic components being for beneficial, negative forcing, and everything else being subsulfated, being the other way. And so I'm just wondering, is it true?
We think that there is a very wide range, and when we look across sort of the multi-model studies, that some of which have tried to include some amount of aging or bleaching, or start with just treatment of brown carbon, but then potentially the bleaching of that over time, that contributes to some of this range of a scaling factor that we apply to the organic carbon forcing.
You have stoves, if people measure the optics of the aerosol that comes out?
Yeah, and what people find is that they are absorbing, there is a significant absorption at first, and within a day or two that tends to go away. So when we think about the mitigation of the global, say the global primary organic positive forcing is about 0.5, when you account for this brown carbon, it might go down to 0.4.
But was it ever 0.5? Was it ever reflecting? Or was it absorbing to begin with, the brown carbon?
Well, I think that's what we're saying. Over the lifetime of the aerosol, which is about a week, that for a while it would have a significant absorption, but then ultimately it is reflecting for the bulk of its lifetime. And so the integrated effect would be a positive. But both of those factors contribute to the range of values. I didn't show here a range by species, but if we did, you'd see that there's a positive and negative range for the organic carbon.
From models or measurements?
This is based on models, but they're being parameterized based on measurements.
I'd love to get some of this data and follow up.
Okay. Yes.
For the ozone concentration response, were you able to break out how much of the increase in premature deaths was caused by lowering the counterfactual or lower concentration cutoff?
Yeah, so we did this calculation every which way. So there's another term in this equation that I haven't discussed too much. It's this bar LCC. So that when we look at this delta in concentration, we can either consider all ozone or ozone above a particular threshold. And so this baseline threshold is what's called the lower concentration cutoff, or sometimes called the counterfactual. Like there's some natural background, and we're not going to assume that exposure below that causes any damage. What that natural background should be is a frequent topic of conversation. One way that it could be defined is the lowest concentration that was observed in the epidemiological study used to derive this data. And so that's the number that's reported here. And so the newer study in the US more recently, we've witnessed lower concentrations, so this counterfactual has gone down. But if you go back and redo these calculations and mix and match these numbers, it can change the estimate of this concentration here that we see by essentially that range. There's some uncertainty there that's driven by, well, I guess that black bar is a combination of these uncertainties, just in terms of the effects estimate alone, and also uncertainties in the counterfactual. So it does make a difference. It doesn't make a big difference in the big picture story, which is, I think, ozone deaths are probably underestimated by at least a factor or two. But as far as the details of how we model that, yeah, I think it warrants more care. Yeah.
Somewhat of a follow-up question of ours about calculating sensitivity of exposure. I have a number of thoughts, but just very quickly. Oftentimes in a polluted place, let's say Los Angeles, Houston, they might co-vary. I had elevated ozone at the same time that I had elevated PM.
Yeah, it's a really good question, and it's an important question. So in these studies, when they look at the explained fraction of the mortalities, they will account for PM, and they'll account for NO2 as well when trying to tease out an ozone impact. And then when they tease out a health impact for PM, they will account for ozone and they'll account for NO2. Mm-hmm. Yeah, so if this seems circular, it is a little bit circular, and it's sort of an iterative refinement process where you try to account for one and account for the other, but there's these very strong correlations in time and space between the exposures, and if you don't try to tease that out, you can get overinflated effect estimates. I get, the statistics gets over my head at some point when you talk to the epi folks, and how that's really, really accounted for, I think, is something that is something that they keep coming back and saying we would like to be doing this better. So I think it could be done better.
There might be a seasonal component to the analysis where in the wintertime when you have maybe lower evaluators and higher with an ozone out there, you can start to isolate just that fact that in summertime they could be a lot of vigorous places. I don't know.
I mean, some of these, they just use summertime ozone anyways. They weren't even looking in the winter. But yeah, there's I think ways that those could be separated. That's the noise my phone makes when there's like a flood.
There's an amber alert.
There's an amber alert. Okay.
Sorry.
All right. If there's other questions, I'm local, and Forrest is even more local, so of course we can chat later. And thank you for your attention.